Of course, today I sent messages initially that I was going to hold today's lecture remotely. I'm going to return to in person on Monday. Okay, so give me 1 second. I'm actually going to share my lecture slide. Okay, this is my lecture slide. Um, of course, we started time series analysis the other time. And of course, in today's class, this is going to be part 7, okay, in the series of the lectures we started on time series. So today I'm actually going to walk you through some examples in real life practical situation. So that's why I call this a case study. Okay, so in a case study today, I basically, I want to use Minnesota, take a look at it, the study of Arctic sea ice extent. Okay, the sea ice extent is can be defined as the area of sea, that has more than 50% ice. Okay, and going by the satellite images, scientists actually record the ice extents. Okay, as you can actually see here, you can from these images taken in 2019, okay, April 29, you can see Greenland, you can see Russia, Alaska, Canada, and the like, right? Okay, so now the focus here is just like we want to see the sea ice extent. We want to be able to see that it fluctuates over time, like even it fluctuates seasonally, and they observe that it reached the largest amount in February or March and shrink to the least amount in September. Of course, we all know the reason why the sea ice actually reached the largest amount in February and March, because we know that actually fall on in the winter time, and shrinking to the least amount in September. We all know September. So because of that, we're going to use the September sea ice extent data from 1979 to 2018, for the analysis. So we want to be able to apply this time series model that we have done in this class. This is more or less like taking you through the real life application of the time series models we've been doing. Okay, so now, well, this is the data set, we got this as the data set, don't forget, we're going to be focusing on the extents, okay? Even though we got a lot of variables in the data set, but we're going to be focusing on the extents, okay? So we're going to be focusing on the extents, and you know what? If I have data frame and I basically want to, you know, extract the variable of interest. Of course, if I use this to read the data in CSV, the name of the data is actually Arctic sea ice. And what I'm interested in is the extent. Don't forget, I'm just going to write the $$ extent, and I'm basically going to be calling that ice. Okay. So which means what we want to study here is to look at the ice over time, right? To look at the trend and stuff like that. So that's what we are seeking to do. Okay, I told you the other time, the very first, the preliminary part of the investigation when you are dealing with a time series is to generate a time plot. So when you take a look at the, this particular code here, okay, this is a code in R. Okay, if I want to plot, can generate a time series plot. Okay, on the highs, don't forget, this is my highs, and the highs is just the extent, okay, the extent in the entire data. I need everyone to confirm again if you're hearing me clearly. Is everyone hearing me clearly?
Yes.
Okay, before I go to the next one, I need someone to confirm if you saw the message that I sent in the announcement section that the lecture today will be aired remotely. I need someone to confirm if you
Yep,
got, okay.
we all got the message.
Oh, okay. Thank you so much for confirming that. Okay, so now the next thing I want to talk about now, we're gonna plot this. Want to say, oh my God, let's take a look at that. Look at that. The reason why we generating this kind of, I mean, the time plot, right? Well, generating the time plot, we basically want to see, looking at it, whether does the mean changes over time, does the variance changes over time. Don't forget that one of the assumptions in time series is stationarity. And what stationarity implies is that the mean has to be the same over time, and the variance has to be constant over time. And of course, that is why the very first point of call is to generate a time series plot. That is, where we're gonna start from. Okay, so and as you can see, right now, okay, I said, can I fit a time series model to this data? Okay, now, of course, I need to check for stationarity. Okay, now, and if I want to do that, of course, if you take a look at what you have here, you may be basically, you're thinking that, oh, there's a kind of, this is not looking like constant over time in a way, but but we have a way to actually investigate all of that. You get what I mean? Okay, now I said when building a model, okay, we would like the nature of the relationship to stay stable over time. Having the nature of the relationship to stay stable over time is stationarity. That's going to be the assumption, like, okay, the mean and the variance have to be constant over time. Okay, and I said that why we couldn't use a model build from early values to forecast the relationship later. Okay, because I told you the other time, every model in statistics has assumption, and what make a model to be super great is when assumption hold. And that is the reason why, if I want to analyze time series data, I think the very first point of call is basically to investigate for stationarity. And how to investigate for stationarity, you can actually generate a time series plot for you to be able to see the behavior of the series over time. Okay, now, so that is the reason that why that happened. Now, as you can see, initially, I told you, take a look at this guy. It doesn't look stable. It doesn't look stable. Okay, because this is like changing. This is not constant over time. I'm actually seeing a kind of decreasing trend here, and because of that, I'm actually going to say there's a violation of stationarity assumption, and of course, when it's a violation of stationarity assumption, you know we have an intervention in the name of differencing. Okay, in this class, I walk you through differencing. The idea of differencing is basically going to come in. Okay, can you just give me 1 second? Just 1 second. Thank you so much. Okay, thank you so much. Can you confirm again if you're hearing me clearly?
Yeah, we can hear and see the presentation.
Okay, thank you so much for confirming that. Okay, so because that was a problem, that we saw, and we need to first fix that problem before we can actually fit our time series models. Otherwise, it's going to be an exercise in futility. Okay, so we're actually going to difference, if you take a look at what I have here. Okay, this is differentiating to lag one. Okay, so when I difference to lag one, then I'm actually going to generate a plot again, to be able to see. Okay, so take a look at this now. So I think this is looking stable now. Okay, it is only when um you realize stability in the process, okay, that you can actually think of fitting time series model. Otherwise, yeah, like I said, it's basically going to be an exercise in futility. Okay, if you compare this guy now, to what we had before, okay, you're basically going to see that this is stable over time compared to the one we have initially that was decreasing trend, that have a decreasing trend. Okay, so now we can say, like, taking the difference at lag one help us to remove the obvious violation of stationarity. Of course, you need to always do that. Okay, and let me tell you this. It is not all the time. That doing that to lag one. Okay, may work. Okay, at times, it may require that you actually go to lag two, in your differencing. But right now, this is looking stable. Okay, and because it's looking stable, of course, we actually going to stop at the like one differencing. Okay, so now that the next thing we're going to do is, don't forget the way we always do. Okay, we're going to generate the ACF plot for the series. Okay, don't forget that the ACF plot we're generating now is for the difference data, not to the original one. Okay, don't forget we difference at lag one, we generate that. Okay, and when we generate that, the autocorrelation function plot, we also generate the partial autocorrelation function plot. Okay, now, if you take a look at what I have now, okay, you basically, I got to plot that are, kind of suggesting more than one model. Okay, I'm going to tell you this. We got situation whereby, uh, based on what the ACF plot and the partial autocorrelation function plot reveal, it may reveal more than one model. Okay, now I'm going to tell you that, that was the reason why I actually, uh, you know, the MA of other one. Oh, give me 1 second. I think that I have a sound in my house.
Not the breakfast, it's burning.
You say what?
Not your breakfast, it's burning.
What is Bunny?
It sounds like your breakfast is burning.
Oh, okay. Give me 1 second. Thank you so much.
I don't think he got the joke.
What was sounding the other time?
It's
This one? Oh, okay. Can you confirm again if you're hearing me clearly?
We can hear and see.
Okay, thank you so much. I think everything is under control now. Okay, now if you take a look at this here, okay, when the ACF plot cut off at a particular lag, okay, if you want to go by what we did yesterday, that's going to be a main model, right? Okay, now if you actually take a look at, you know, what we have, you know, when you take a look at the ACF plot here, you know, after, you know, the lag one, okay, after the lag one, this is the lag one, okay, it's cut off, right? Okay, this is a lag one, there's a one here, right? It's cut off, okay, that is suggesting MA1. And if you come to the PACF, don't forget when the PACF cut off, okay, the PACF cutoff is going to support the autoregressive model. Okay, now you're going to see that after lag one here, okay, it's cut off. Okay, and not only that, I cut off after lag one, even after lag three, you know, this one, you know, this one is corresponding to 3. After lag 3, cut off as well. So the PACF here is giving us the idea of AR1 and AR3, and the ACF plot is actually suggesting MA of order 1. Now, when you take a look at, you know, we can have a situation whereby our plot could reveal more than one model. Okay, now we got, because of that, because we got more than one model, we're basically going to call them 3 candidate models. They are competing now, and we need to figure out which one is the best among the 3. Okay, I need someone again to confirm, you know, if you really understand how I use the ACF plot and PACF plot, you know, how that actually lead me to, you know, to be suggesting MA1, AR1, and AR3. If you really understand that, can you say yes, or you comment yes, or you give me a thumbs up? I'm going to ask the question again. If you really understand the way I figured this out, I need you to say yes, or you comment yes.
Yes,
Okay, okay, but is there anyone who doesn't understand how I figure it out? Is there anyone who doesn't understand how the 2 plots here actually suggested these candidate models? Is there anyone who doesn't understand that based on what we've learned in this class? Is there anyone? Okay, I'm gonna say that again. Like, if you take a look at this ACF plot, okay, when ACF plot does not decay to 0, when ACF plot is now performing a function of cutting off, that's an MA. Okay, here now, this is at lag 1, right? And it's cut off after lag 1. When MA, when ACF plot cut off, okay, that will suggest an MA model. And it cut off at lag 1 here, then that's why MA1. But when you take a look at the PACF plot, you know, when a PACF, a partial autocorrelation function plot cut off, okay, is basically going to indicate autoregressive model. But this actually cut off in 2 different occasions. Okay, if our first cut off, this is at lag 1, you know, you're going to see immediately after lag 1, every other one fall within 0. But if you take a look at this again at lag 3, it cut off again. So which means it cut off in after lag, you know, after lag 1 and after lag 3. So that is why we have AR1 and AR3. And you know what, we got 3 candidate models now. We got 3 candidate models now. Okay, now, you know, at times in statistical analysis, we could have more than one model. And of course, we got criteria to identify which one is the best. Okay, now we got 3 models now. Now, we got 3 models now. We're going to fit each of them to our data set. Okay, don't forget, we're going to start by fitting the MA of order 1. We're going to fit autoregressive model of order 1. We're also going to fit autoregressive model of order 3. Okay, so this is the coding now. You know, if I want to fit autoregressive model of, the moving average model of order 1, the moving average model of order 1 is 001. Don't forget, I said something yesterday, you know, we're using ARIMA. Okay, so when I have ARIMA, Okay, I can split that into three. Okay, where I got the AR aspect. Okay, the AR aspect is basically going to have P order, and I, which is what we call the integrated order, the one that is doing differencing, okay, is of order D, and the MA is of order Q. Now, when I'm considering MA of order 1, it's actually mean I'm not considering, I'm considering a zero order in AR and a zero order in the differencing and 1 in the MA. So that was why you see 001. And in the end, we actually we got a result. So this is the output now. Okay, what you're seeing here is the output. Okay, and of course, based on the output, we're basically going to write the fitted model. Okay, now based on the output, we can write the fitted model. But you know what? Let me now go to the arrow of order 1. For the arrow of order 1, of course, there's going to be 100. I have an output as well. Then I'm going to go to a arrow of order 3. For the AR of order 3, it's just going to be 3,00. But don't forget, in each of the AR, okay, we're using a difference data. Don't forget, initially, the data set was actually problematic, or problematic in the sense that that was a violation of stationarity. Okay, that was a violation of stationarity, and of course, we difference that to lag 1. That was why you're seeing DIF1. When I take you back, okay, you can see that we call that DIF1. Okay, so that was the reason. So the data set that we're actually using is a difference 1 to the lag 1. Okay. Okay, so we've run all that in R. We're basically gonna have 3 separate R outputs. Okay, now if we have that, what we're gonna do now. Okay, just like what we always do. Okay, we can investigate. The initially you know the autocorrelation function plot and the partial autocorrelation function plot actually suggested 3 models. We've run them, and you know what we want to do now? We want to conduct a residual analysis on the 3 models. Okay, I told you the other time in statistical analysis, we actually have a preliminary investigation. As part of the preliminary investigation, we generate plots, and after we are done with the analysis, they're basically going to be post hoc analysis. In the post hoc analysis is when you conduct what I call the diagnostic, when you subject your model to diagnostic testing. You basically want to validate your model. Okay, so because of that, this is a point. When we're trying to validate, we're actually going to generate autocorrelation function plot of the residual. I told you the other time, there's a difference between autocorrelation function plot of the time series data and the autocorrelation function plot of the residual. Okay, in the autocorrelation function plot for residual, is more or less to investigate whether residual behave like a white noise. Residual would behave like a white noise if the autocorrelation value at different lag, or they all fall within 0. Okay, for the MA1, what you see now, okay, you're going to see they all fall within 0. I always told you, I told you the other time, at lag 0 is always going to be 1. It doesn't really matter. Okay, so what is this guy telling me now? Okay, this guy is trying to tell me MA of order 1 is appropriate. Okay, the MA of order 1 was suggested initially, and you know what, we have validated the MA of order 1 now using the autocorrelation function plot of the residual. We're also going to do the same for the other candidate model. Okay, for the other candidate model, I need you to take a look at the AR1 now. This is the same thing. Okay, the white noise, the residual behave like a white noise. In the ARO of order 1, the residual also behave like a white noise. In the MA of order 1, then we're going to look at that of ARO of order 3. Don't forget, we actually at the candidate model. Oh my God, in all the models suggested, where the residual behave like a white noise in each of that. Okay. And that was why I asked a question, what of in exam? I gave you a picture like this and I said, do the residual behave like a white noise? The answer is yes. The residual behave like a white noise, apart from the autocorrelation at like 0, every other one actually fall within the blue dotted line. You see the blue dotted line, if something fall within the region of the blue dotted line, that indicate the autocorrelation value is approximately 0. Can you see confirm again if you're still hearing me clearly? Is everyone still hearing me?
Yes.
Okay, thank you so much. And thank you for confirming that. Is there any question at this time? Is there any question? Okay, in the absence of question, it means you guys are good. Okay, as you can see, the 3 models suggested, the candidate models, okay, residual in each of that behave like a white noise. Okay, we just investigated that. Okay, so that was why I add this conclusion now. All of these models are valid. But let me tell you, if all the models are valid, a statisticians or the data analysts, they are at a road. It's like a crossroad, right? They basically need to choose the best. Right now, all the 3 models, okay, they pass several tests, just like in your company, you need you want to employ one person, okay, a role, a particular position is vacant, and you want to employ one person, and you have screened a good number of applicants, up to 3. We got 3 applicants in the, in the final standing, and of course, basically want to figure out the best among them. But right now, up to this stage, they are all looking promising. But you know what? You don't have a position. You don't have position for 3. It's only one position that is vacant, and which means, can we have other model selection criteria and statistics that we can actually apply to figure out which one is the best? Because there's basically going to be the best among them, even though the 3 can do the job, but we basically need one, that we actually stand out among them. So because of that, we now need to compare the AIC. Okay, we're going to compare the AIC. This is the AIC. Okay, some of you may be wondering, where do we have AIC as part of the our output? Let's go back. I'm going to show you now. There's always going to be that. Take a look at this guy here. Do you see that? Okay, when you run the coding out, the AIC is going to be automatically generated. It's going to be part of the output for each model that you run. You're basically going to have the AIC. Okay, the AIC is what we call the archaic information criterion. Okay, so you can see that every output is basically going to have the AIC. And let me tell you this, AIC is one of the model selection criteria in statistics. A model with the lowest AIC is deemed to be the best model. Okay, a model with the lowest AIC, okay, is actually going to be regarded as the best model. As you can see right now, okay, the model with the lowest AIC is actually the MA of other one. Okay, take a look at that. So in a situation where if you find yourself in this kind of situation where the models actually pass a lot of tests, and you basically want to decide among them which one is the most appropriate, because there's always going to be the most appropriate, okay, among the competing models. Okay, and that is why you're actually going to use AIC. And if you take a look at this particular column now, it's just telling you the numbers of parameters in each module. Of course, in MA1, you're going to have 2 parameters. Don't forget, the 2 parameters, don't forget the MA1, you are relating the current, okay, the current values of the series to the current current white noise and the immediate past white noise. Okay, so we're actually going to have 2 parameters in that regard. And of course, in the autoregressive module of order 1, there's going to be 2 parameters. You remember the C0 and the C1, right? Okay, the C0 and the C1, right? Okay, so the C0, the C1, okay, that's what is making it 2. And don't forget, the autoregressive module of order 1 is giving an impression that you are trying to tell the world the future is a replica of the past, like the future resemble the past. That's what you mean. In the autoregressive module of order 1, you are actually relating the current values of the series to the immediate past. And of course, in the autoregressive module of order 3, okay, when you see order 3 now, okay, you are actually relating the current value of the series to the 3 previous paths. 3 previous paths. Okay, with the intercept, that's why you're going to have 4 numbers of parameters. And you know what, going by the AIC now, okay, the MA1 or MA of order 1 actually stand out. The model with the lowest AIC is actually the best model. Okay, that's what we do all the time. When you actually comparing models, okay, you're actually going to use AIC. Okay, the one with the lowest AIC is actually the best model. So which means right now, what we're telling the world, the best model is the MA of order 1. Okay, you remember I told you something yesterday that, prior to 2008, we were using autoregressive model. Okay, the autoregressive model did not alert investors, did not alert the world that there was going to be a global financial crisis in 2008, because the autoregressive model was giving us the idea that, okay, 2008 is basically going to resemble the past, but we all know that did not happen. Okay, because in 2008 there was global financial crisis. The United States stock firms actually have a lot of issue. Not only that, even in the world, okay, because of the fact that we use a wrong model. Okay, when you use a wrong model, of course, we basically going to mislead, and we don't want a situation whereby we're basically going to be where that is going to happen. Where that happen, okay, we're going to be in trouble. And that is the reason why we basically need to exploit, we need to exploit in data analysis and statistical analysis. We need to make sure we exploit, the different kind of models available. And among them, we got a way to use a model selection criteria to be able to come with the best model. Okay, right now, out of the 3 models, the MA of order 1, I want to believe if the moving average model was used before 2008, I want to believe that that would have alerted investors ahead of time, because the MA, the moving average model, is trying to say, okay, you know what, the current does not, the future does not resemble the past. And if I'm using moving average model, I believe I will be able to predict the current, putting into consideration the current white noise and the past white noises. That is what that means. Okay, based on this now, we're basically choosing the MA of order 1. Okay, so that's why I said so the MA of order 1 has the lowest AIC, and that should be actually preferred. Okay, now if I don't want to make a prediction now, making a prediction, I want to believe, 2000 and prior to 2008, they made a prediction ahead. believing that everything was going to be fine in 2008, but we all know what happened. Okay, we use model that misled the world. Okay, so we want to make prediction with the MA now, MA of order 1. Okay, with predict functioning now. Okay, as you can see, we got a code here, right? Oh, give me 1 second. Okay, so this is the code, right? Okay, so this is the code. Okay, MA1. Okay, end order head 1. Okay, now when we do that, you're basically gonna have 2 different output, one for predict and the other one for the standard error of that. But you know what? What we basically, this guy that came out, okay, is actually data Y40. Okay, that is data Y40. Okay, so if that guy is data Y40, okay, don't forget what do we want to predict? We want to predict for 41 data point. Our data actually ended in 40. Okay, the data set we use ended in 40. Okay, and we want to predict for 41, like the next, if it is day, the next day, if it is year, the following year, if it is month, the following month. Okay, and you know what, I want to figure out days, but you know what I know based on what I showed you yesterday, the data Y40 is Y41 minus Y40. Okay, and I already got this guy from the code, the one. Okay, so all I'm just gonna do, okay, is I can solve for this where I'm actually going to have this equal to this guy, right? Now this guy now is the one that I got from there, and the Y40 is going to be the last data point. Okay, the last data point. If you really want to get that, you can actually use this code here on the highs, the original data highs before you difference. Okay, the last data point was 4.71. Okay, by the time you plug that in, okay, this is our prediction now. That's our prediction value. Okay, that's our prediction value. Okay, so 4.45 now is our predicted value. Take a look at that. Is there anyone who want to ask question or any clarification? Or now I got my prediction. Is there anyone? I need someone to confirm again if you're still hearing me clearly. Is everyone still hearing me clearly?
Yes. I did actually have a question. So
Yeah, go ahead.
when you get what would you use the standard error predicted value for?
Okay. You mean when it is time to use standard error, right?
Yes.
Yeah. In case we want to figure out, maybe we want to conduct a statistical significant test, or we want to look at the confidence interval. Okay, so the standard error will be used, but right now we don't use it. Does that make sense?
Yes.
Okay, that's a very good question. Okay, now let us now, with choosing MA of order 1, we make prediction with that. We know we can also try and say the other modus, okay, that we did not choose based on the AIC. Let us see the model. This is the feeder model for AR03. This is the feeder model. I'm writing that. Don't forget this is the mu, right? 0.007. Okay. If you go back to the AR for that 3, the output for AR for that 3. Okay. Do you see this guy? The intercept, I told you it's always the mu, right? That's the estimate of the mu, right? Don't forget that. Okay, so the ARO for that 3. This is the ARO for that 3. If I want to use the ARO of order 3 to predict now, I've used the MA of order 1, okay, to make the prediction. Okay, if I now want to use the AR of order 3, okay, these are the feeder model. Of course, you all know how where this guy, and where this guy come from, right? They all come from here. Let me take you back in case you don't know. AR of order 3. This is them. Do you see that? Do you see that? They all come from there. We chose to 2 decimal, right? Okay. I believe you understand that now, right? Okay, now, since they all came from there, I want to make an attempt to use a arrow of order 3 now to actually, now if I want to use a arrow of order 3, don't forget, why do we have all this data? We have all this data because of the fact that we difference to lag 1. Please don't forget that, because we difference to lag 1. That was why we got data there, you know, all this data. Otherwise, if you don't difference, the data is not going to be there. Okay, take a look at that. Now, I want to predict for, we want to make a prediction for 41. Okay, now, if I come here, if I plug in 40, okay, see to be 40, that cannot be 40, right? 40 minus 139, 38, 37. Okay, when I, so which means from here now, I can determine this guy, right? And how am I going to determine this guy? I'm actually going to go back and, you know, go to the difference. Okay, to the difference, I need data point 37 to 39. Don't forget the difference. Okay, I need 37, I need 38, I need 39 in my difference data. Okay, and that is going to give me all this. Then I'm basically going to plug in here, and here. When I do that, I'm actually going to get I'm going to get this guy out. Okay, when I get that guy out, okay, so like I said, you know, that is all what all those ones stand for. Does that make sense? That's all those ones stand for. Then when I plug them in, like I said, that will enable me to figure this guy out. When I figure this guy out, the next thing now is, what is the ice? What is it, you know, in the data test that is not difference, the 40 is going to be 4.71. And I'm going to use the, then I can get this guy out. Okay, don't forget, like Y40. Okay, if this guy, the Y40 is this guy, then what I want to do, I want to do Y41, right? So Y41, okay, is basically, you know, Y41 is basically going to be this and that. So that is the reason. So take a look at that now. Give me 1 second. You see that now? You see the relationship? I need to first figure out this guy. So this guy was figured out from the model. We figured this guy out from the model. And this is the last data point in the original data point. I plug that in, and that give me 4.49. Okay, take a look at this. The MA of order 1 give 4.45. MA of order 1 give 4.45. But A arrow of order 3 predicted 4.49. Okay, predicted 4.49. Okay, you know, why, once again, why do I actually use two models? If you go back to the AIC, okay, using the fact that this guy, MA of order 1 is the best, the next one is going to be arrow of order 3. So the best two models here is AMA of order 1 and ARO of order 3, even though we know MA of order 1 is the best, but ARO of order 3 is the second fiddle, okay, the second best. Okay, you all see what came out of their prediction. Their prediction is very close. Is there any question? Because this is going to be the final, this is going to be the end of my lecture today. Is there any question? Is there any question? Okay, I'm going to return to in-person arrangements on Monday. And let me tell you, this week, you're going to see your result for the midterm too. I'm also going to release practice our final question. And watch out today on the announcement section. You're going to see the final. I'm going to tell you the area the final is going to cover. And I'm also going to walk you through the practice question. Okay, so on Monday, the final, that topic is going to become, it's not going to be, you know, the topic that I want to introduce you to on Monday will not feature in the final. It's just an addendum. We call it panel data. The panel data, you know, we've been working with one entity, one firm, right? What if in a situation where I collected time series data over the years and across countries or across firms or across individuals, okay, I'm going to tell you the method we've been applying is going to fail. We can't use the method. So how we call that panel data, panel economy entries. You know, the panel now implies that I collected data set, the time series data over time and over cross-sectional unit. That is what I'm going to walk you through in class on Monday. But that is not going to be part of the final at all. Like I said today, watch out. There's going to be a series of announcements that will be coming in. Okay, is there anyone want to ask question? And for those of you who actually reach out to me, I send a message to some students that actually want to see them, that they should set up an appointment with me. I'm actually going to reply. I've seen some of your messages. Okay, I need some to actually set up an appointment with me because I've been seeing some stuff and I want to meet them virtually. Okay, on the Zoom. You can be anywhere in the world, to have a meeting with me. Okay, so, and I'm also going to say this, those of you that joined class lately, and maybe you are missing one or two assignments, you can actually ask for makeup. Those who have asked for makeup, I'm basically going to reply to their question today. And not only that, maybe you miss midterm 1 or midterm 2. I'm flexible. Okay, you can ask for makeup. Okay, somebody said I have an appointment. Okay, when is your appointment? I think I saw a chart now. I'll say I have an appointment. Do you say I have an appointment or do you want to schedule an appointment? The person that chat with me right now. I need clarification from the person that chat with me right now. I can see you in the chat. You said I have an appointment. Is the person hearing me? I saw it in the chat. The person said I have an appointment. Can the person talk or person chat to clarify that? Oh, maybe the person is no longer in this meeting. Okay. That is what I have for you today. Make sure you all stay safe and have a beautiful day. Bye for now, everyone.
Thank you. See you next week. Have a
See you
good
next
week.
week too. Yeah, thank you. Yeah. All right.